This question is about polarization. State what's meant by polarized light. Light for which the electric field vector oscillates in only one plane. Okay. Light of intensity I0 is incident on a polarizer. The transmission axis of the polarizer is vertical. The polarizer is rotated by an angle theta about the direction of the incident light. The intensity of the transmitted light is measured. So sketch graphs to show the variation of transmitted intensity I with theta when the incident light is horizontally polarized. This is the situation where we can apply Malus's law. So I is equal to, I is equal to I0 cos squared theta. In this case, it depends a little bit on how it's shining initially, but we might, for example, start off with it exactly crossed. Oh no, it says horizontally polarized, and this is lined vertically, which means that nothing's going to get through to begin with. So we're right, we should have a zero intensity initially, and when we've turned it by 90 degrees, then the polarizer is going to be vertical, so then we're going to get all of it coming through. And then when we've gone around 180, then we're back to where we started with no intensity getting through. And it's going to go something like this, because it should be in the shape of a squared sinusoid. So that's not a very good representation of that. So let's just rub that out and try again. So we're heading towards that point. Something like that. Okay. When the incident light is unpolarized, there was a multi-choice question that was almost exactly the same as this. When the incident light is unpolarized, we're always going to get 50% of the light getting through, because there's no preference between the horizontal polarization and the vertical polarization for unpolarized light, and the polarizer is always going to remove all of one component and leave all of the other component. So 50% of the light will get through. This question is about the interference of sound waves. Two loudspeakers, S1 and S2, each emit a musical note of frequency 2.5 kilohertz with identical signal amplitude. Point P lies on the line AB. Yep. The speakers are placed 1.5 meters apart from each other and 8 meters from the line AB. Okay. A person walking, hold on, let me just get rid of that. A person walking in a straight line from A to B observes that the intensity of sound waves alternates between high and low. With reference to interference, explain why the intensity of sound waves alternates along the line AB. Okay. So, sound from the two speakers have traveled different distances to reach any point on the line. At positions where this path difference is n lambda, n equals 0, 1, 2, 3, etc. Constructive interference occurs. Producing sound waves of double amplitude. Okay. Okay, and then where path difference is n plus a half lambda, we get destructive interference, which leads to no sound. Okay, so you can expand that last point a bit. The bit that I realize that I've left out here, I don't have any space to add it in, but the bit that I've left out is that we should also say that at these places here, where we have n lambda, we say that the two waves will arrive there in phase. And here, because the path difference is an odd number of half wavelengths, we say that these are out of phase. Okay. The sound has a maximum intensity at P. Calculate the distance along line AB to the next intensity maximum when S1 and S2 emit a musical note of frequency 2.5 kilohertz. Let's find out where that point P was. P is right in the middle. Okay. So the speed of sound, so we need to work out the wavelength of the sound. Lambda is equal to I surely would have given more information. Are we supposed to calculate all of that in that little space and only get 2 marks for it? They're 1.5 meters apart, 8 meters away. I guess so. 330 meters per second is the speed of sound we're given. Okay, let's do it. Okay, lambda we can get because v is equal to f lambda, so v over f will give us lambda. And that is equal to 330 over 2.5 times 10 to the 3. Let's work out what that is. Oops, that was 220. Where's my clear button? There. 330 divided by 2.5 times 10 to the power of 3 is 0.132 is the wavelength. Come on. Equals 0.132 meters or 13.2 centimeters. Okay, so and for the next maximum, so the path difference has to be a whole wavelength. Equals PD for next max. S equals lambda D over D, where S is the separation of maxima. So this is S, and this is D, the distance, this distance here is D, and the separation here is little d. Oops, this should be big D. Okay, so then we can say that S is equal to lambda D over D, which is equal to, well, we just worked it out, it's 0.132 times big D, which is 8 over 1.5, which is equal to, so up a bit, 0.132 times 8 divided by 1.5 equals 0.704. Okay, that is only true if we assume that this angle is small, which it sort of is. It's not going to be the most accurate, so maybe we should reduce the number of significant figures here so that it reflects our accuracy. So that's 0.70 meters. Okay, so technically, in these situations, if we suspect that the angle is big, we should use n lambda is equal to d sine theta, where theta is that angle there. However, given the amount of marks that we have available for us in this question, it's probably not necessary to do that. Okay, S1 and S2 are moved so that they're now 3 meters apart. They remain at the same distance from line AB. Discuss the changes, if any, in the rate at which the intensity of sound alternates when a person is walking along the line AB at half the speed. At half the speed. Okay, so they're moving them further apart. Further apart increases D. Assuming what's our equation? S equals lambda D over D, doubling D will have S. So maxima are half as far apart. Having S, so, and if speed is also halved, so we made them half as far apart, but we also halved the rate at which we're walking. So the sound alternation won't change. Okay. So you need to bring in the equation to show that you fully understood.